Good morning, everyone. My name is Shreya, as you just saw, and I'm representing the Grossman Group from the Department of Material Science and Engineering. We are a team of computational and experimental material designers looking to make water filtration, water desalination cheaper, better, faster by redesigning the membrane that's used for separation. So desalination is growing worldwide, particularly in industrial areas. In Singapore, 25% of the water demand is met by desalination and another 30% from reclaimed wastewater. The largest concentration of desalination is in the Middle East, where in Saudi Arabia, 70% of the water is desalinated water. Reverse osmosis, or RO, uses pressure-driven flow to force water across a semi-permeable membrane that rejects salt and produces fresh water. The market for these RO membranes is expected to reach $2.8 billion by 2020. So the cost of desalination has come down, especially since the 80s, when thermal desalination methods were the predominant technology. Thermal means that your input energy is heat as opposed to electricity, as it is for RO. But it's still many times more expensive than traditional groundwater supply measures, sometimes up to 10 times more expensive than if you were to pull fresh water directly. And why is it expensive? It's expensive for two main reasons: energy and capital infrastructure. 44% of the cost of desalinated water is based on the need to maintain a very high pressure in order to force that water across the membrane. Another 35% of that goes into the construction and maintenance of the infrastructure that contains many tens of thousands of pressure vessels to contain these membrane cartridges. Reverse osmosis is the most energy efficient desalination technology, using less than a third of some of the thermal desalination technologies, third of the energy of some of the other thermal desalination technologies, but it's still above the theoretical minimum work of separation in order to remove the salt from the water. The cost has come down, the energy has come down. A lot of those improvements have been a result of system-level efficiency improvements, ingenious plant design, but the inherent performance of the membrane has remained pretty constant. So we, as material scientists, took a look at this and said, let's look at the material of the membrane. It's the point in the process where the most entropy is generated, and let's see how we can redesign the membrane to kind of address those cost concerns. So in 2011, my colleague David, using computational molecular dynamic simulations, was able to look at the properties of different materials and identify nanoporous graphene as the ultimate membrane material. Graphene, as you may know, is the arrangement of a single layer sheet of carbon atoms. It's the graphite from your pencil lead, but it's one layer, it's atomically thin, it has very unique characteristics, and is studied extensively for electronics, optoelectronics, touch screens for smartphones and televisions in the electronics industry. We are looking at graphene from the perspective of water, and we're looking at it specifically for water desalination and have filed intellectual property around graphene, nanoporous graphene, as a desalination membrane. So thanks to its unique pore chemistry, its atomic thinness, its surface properties, and very precise sized holes, we expect graphene to exhibit permeabilities, or the passage of water with respect to time and pressure, that are 10 to 100 times that of conventional RO membranes that are in use today. But what does that mean? That means a completely different set of operating parameters at the plant level, so at the operator level of the plant. We kind of see our membranes as being used initially as a plug-and-play technology for the membrane cartridges that are already used in desalination plants and are replaced on the order of 3 to 5 years. So in this plug-and-play configuration, we can cut costs in 3 different ways. The first is higher throughput, or more water desalinated per day, which means more revenue generated for a given capital investment. Similarly, it means that if we were to design a new plant and to meet a specific water demand, it would need to be smaller because you have more water desalinated per day. The second is lower energy through lower pressure requirements approaching that theoretical minimum of work of separation. And the third is higher recovery, or more fresh water generated per unit input salt water. This is important because the cost of disposal of that highly concentrated brine solution is another cost component within desalination. So what we looked at when we started looking at costs is we found that we don't actually need the 10 or the 100 times more permeable membranes. In fact, a 3 times increase in permeability in membranes could cut capital costs by up to 63%, or energy costs by up to 46% for brackish water desalination. So can we make these membranes? How are we making these membranes? We have experimentalists on our team, myself included, who are looking at the technical feasibility of graphene, nanoporous graphene membranes. We're looking at the problem from 2 different angles. The first is evaluating graphene in the context of water applications, and the second is a scalable method to create very, very precise and very, very small nanopores over large areas of material. So in particular, we are using computations to study graphene, how it rips, and design the size and morphology of the support structure that the active layer would rest on. We are looking at multiple promising approaches to create nanopores, again, scalable methods to create nanopores in materials at a size scale that has not been accomplished yet today in any type of industry process. And our lab is outfitted to be able to test membranes for permeability, look very, very closely at their performance of our membranes and compare them with today's commercial membranes in order to demonstrate the selectivity as well as the increased permeability of our fabricated membranes. So looking forward, we're very excited about our project. We're very much looking forward to the next few years of work on this project. I would like to extend a thank you to the Deshpande Center and our catalyst Andre, and Leon, and everybody else. And we're feeling very glad to be here and look forward to hearing your questions at our poster. So thank you so much.